So for us, we're moving on to theoretical probabilities. So when we do this, we want to be able to calculate theoretical probabilities, and at the root of that is an assumption that is key, and that is that all of the outcomes in the sample space are equally likely. If I roll a die, I'm assuming that all 6 faces are equally likely. If I toss a coin properly so it doesn't spin, I'm assuming that both heads and tails are equally likely. Now, it's easy to forget this, especially when you go out into the world and you say, hey, what's going to happen in a particular situation? Theoretical probability comes with this baked in, the idea that all events are equally likely. Now, there is a way to change this, and we will go through and we will talk about events that have different probabilities. But for now, equally likely. This means that every outcome of an experiment needs to have the same likelihood or chance of happening. So theoretical probabilities look very much like empirical probabilities. We figure out the number of outcomes in the event space. Remember, the event space is the outcomes that we're interested in, that we want to find the probability for. And we divide that by the total number of outcomes. That is the total number of outcomes in the sample space. So let's look at flipping a pair of coins. So here it is. I've been leading up to this. So what is the sample space? Well, 4 things can happen. And at this point, I am going to slow down and talk for a little bit about why that is true. So if I flip a coin, I might get a head, and then I flip it again and I get another head. So that first HH represents the outcome where I get a head and then a second head. The second outcome represents the outcome where I get a head followed by a tail. The third is a tail followed by a head. And the fourth is 2 tails. Now be very clear that the middle 2, the one with 1 head and 1 tail, or I should say the 2 with 1 head and 1 tail, are in fact different outcomes. Each outcome has a 50% chance of getting a head and a 50% chance of getting a tail. But once you toss that first coin and get a head, there's then 2 possibilities for the next coin. In other words, the moment that I know that I've got a head for my first toss, so what I'm doing right now is trying to convince you why there should be 4 events in the sample space. So I'm asking you in these first 2, what are highlighted right now, HH and HT, I'm asking you to notice that once we've flipped the first coin and gotten an H, there's still 2 possibilities for the second coin, an H or a T. And then I'm going to go through exactly that same reasoning for the second pair of outcomes. If when I flip the first coin I get a tail, that doesn't affect the probability of the second outcome. In other words, the fact that I flipped a tail in the first flip, in the 2 outcomes that are now highlighted, that doesn't affect the probability that I'll get a head or a tail in the second flip. In other words, they're still equally likely. So there are in fact 4 possibilities in the sample space. And this is a huge issue, because basically it means that if I now ask you questions about this sample space, I have to notice that there's 2 ways, for example, of getting exactly 1 head. I could get it first or I could get it second. So let's look at this second example. Now, there was something very similar in our warm-up exercise where I asked how many months have 28 days. And that was an example of English not being very exact, not being very precise. So this sentence, however, is very precise. It says, what is the probability of getting exactly 1 head? 1 head and no more. So exactly 1 head. So notice that that first situation where we've got a head followed by another head doesn't apply to this. That's 2 heads, which is not exactly 1 head. And of course, the last situation where we've got 2 tails doesn't apply either, because there's no heads at all. The only things that apply to this question are a head followed by a tail or a tail followed by a head. Those are the only 2 situations out of the 4 in which we get exactly 1 head. So 2 out of 4 is our theoretical probability. We can simplify that to 1/2. The next question, what is the probability of getting at least 1 head? And again, this is an example of English being used more mathematically correctly or more precisely, at least one head. Well, certainly the two we just looked at, HT and TH, have one head, but at least one head opens the possibility of there being more than one. So now we get to count HH, a head followed by a head. So that means of the four in our sample space, 3 of them have at least one head. So I've highlighted those 3. So of the 4, 3 are in our event space. So 3/4, which we can't simplify. So 3/4 because we're now looking at least one head. What is the probability of getting a head and a tail? So what is a head and a tail? Well, that's saying 2/4 again, or 1/2. Now, that's simply saying that we've got a head and a tail. That's exactly the same as the first question. One head, that's what the A means, and one tail. Well, there's 2 ways to do that. Let me change that highlighting up there back to the 2 ways that show us how to get a head and a tail. What is the probability of getting a head or a tail? So that last question is basically defining the word or. So a head or a tail? Well, let's see. In the first outcome, we've got heads and or tails. In the second outcome, we've got heads or tails. In the third outcome, we've got heads or tails. And in the fourth outcome, we've got heads or tails. In fact, that's the only thing in our sample space is our heads or tails. So what's the probability of this? Well, all 4 of the outcomes in our sample space would be in the event space in this case. 4/4 is 1. When you toss a coin, you're going to get heads or tails. So the next thing to look at is probability properties. So the first one is that the probability of any particular event is between 0 and 1. If, now we're looking at the second property, if the probability of event is 1, then it is sure to happen. That probability is a certain event. If I tell you the probability is 100% of something happening, it's going to happen. However, in number 3, it says if the probability of an event is 0, then it cannot happen, and that event is impossible. Now, number 4 is stated fairly poorly. So I want you to look at number 4 simply from the point of view of a kind of intuitive understanding. This says sigma, that's a capital sigma, that means to add up all of the probabilities of all the events, and it says that that's guaranteed to be 1. Now we have to be a little bit careful about that, because what is all the events? So we're talking about all the events that form the sample space. If you simply look at everything in the sample space and add up all of those separately. So we're not making compound events that took maybe 2 things in, or 3 or 4 or several things into consideration. We're looking at simply adding up all the events in the sample space. So that's probably intuitively obvious. Number 4 simply says what's the probability of something happening, and the probability that something's going to happen is 100%. You're not obliged to know too much about playing cards for this. I, for example, know next to nothing about most games of chance that involve playing cards, but having taught statistics, I know a little bit about the playing card deck. So let's go through this quickly. If this is the first time you've seen it, happy days. There's no 1 in the playing card deck. Taking its place is an ace. The ace is abbreviated with an A. So if you look at this first row, the diamonds, you can see that there is no 1. It starts at 2. It goes up to 10. There's then a jack, which you could think of as an 11. There's a queen, which you could think of as a 12. There's a king, kind of like a 13. And then, of course, the ace, you could kind of think of as a 1. And anyone who plays cards knows that that's a kind of sloppy way of doing it. The cards are arranged in this way for a reason. However, notice also that I named one of the suits. So there are 4 suits. Look at the 4 rows and let's talk about that. So that first suit, everything in the first row is diamonds. Below that are the clubs. They look like clovers to be, but they're called clubs. Below that is the appropriately named hearts, and in the bottom row are the spades. So there are 4 suits. The 4 suits, again, are diamonds, clubs, hearts, and spades. Also notice that all 4 suits have the same kind of card. In other words, each of the suits has a 2. Each of the suits has a 3 all the way up to 10, Jack, Queen, King, and Ace. Also notice that there is a color. 2 of the suites are red, that is the diamonds and the hearts, and 2 of the suits are black, that is the clubs and the spades. Okay, that's pretty much all you need to know about playing cards. Each suit has 13 cards. There are 4 of them. 4 times 13 is 52, and so on. So what is the sample space if I were to pull a card from a 52 card deck? And that's kind of a silly question because each card from the entire deck is the sample space. In other words, the sample space is the picture you see above. That's all the possible cards that I could pull from a deck. Now, I could try to be sophisticated, and I kind of got a little bit lazy as I was working through this. You can try to name these and list them. It wouldn't be terribly difficult, but I didn't work through it because I don't think I need to. You can see what's going on here. That first 2D stands for the 2 of diamonds, then the 3 of diamonds, the 4 of diamonds, the 5 of diamonds, and then all the way through to the Jack, Queen, King, and Ace of diamonds, and then the 2 of clubs all the way through the Ace of clubs, and then all the way down there to the Ace of spades. So you could list this, and certainly when we look at more difficult questions, we will do that. Okay, now let's start to ask some questions about this, and I'll be scrolling up and down. I hope that's not too jarring as we do this. It says, what's the probability of getting a spade? So remember, a spade is one of the 4 suits. So when you look at the sample space, you really have a choice in how you look at it. You can look at it as 52 individual cards, or you could look at it as 4 rows for the 4 suits, or as 13 columns for the 13 different numbers and faces. So this is asking us, what's the probability of getting a spade? Well, I'm going to think of taking this as a piece of paper and cutting it into 4 strips. So I'm going to say, hey, there's a strip that's diamonds, a strip that's clubs, a strip that's hearts, and a strip that's spades. I'll turn them over, shuffle them up, and pull one at random. So I'm basically thinking of the 52 card deck as being composed of 4 groups. So what's the probability that I'm going to get a spade? Well, it's 1/4. Now notice that is exactly 13/50 seconds. 13 divided by 52 is 0.25, is a quarter. Okay, now I'm going to ask what the probability is of getting a jack. I'm going to do something similar to the previous question, but instead of dividing the deck up into 4 suits by taking this piece of paper and cutting it into 4 horizontal rows, I'm going to think about taking this piece of paper and cutting it into 13 columns. In other words, there'll be one that's all 4 of the 2s. There's going to be one that's going to be all 4 of the 3s. And of course, what I'm interested in is pulling the one that's all 4 of the jacks. So I've got 13 of these horizontal strips. I turn them over so they're face down. I shuffle them up and I pull one at random. And the question is, what is the probability that I get one of the that I get the jacks? And that is, of course, one of the 13 different faces or numbers that I can get, 1/13. Now let's go back and do this again. Let's do this by thinking about all the cards being independent. There are 4 jacks out of 52 cards. Well, guess what happens if you divide 4 by 52? 4 out of 52 is exactly 1/13. Now, at this point, you might say, well, we've seen 2 examples, one about suits, one about a particular face or number. What would an ace be more like? Well, there are 4 aces, so we could do this the long way. 4 aces out of 52. 4 divided by 52 simplifies, and you can use your calculator for that, to 1/13. And there's some more on the next page. What is the probability of not getting an ace? And here, of course, the important word is not. We're interested in getting anything but an ace. So let's think about what that means. There are 52 cards. 4 of them are aces. So if we take away the aces, 52 minus 4 is 48. There are 48 cards that are not aces. 48 out of 52. But we can think of this by also thinking about each face or number separately. There are 12 faces or numbers that are not an ace out of 13 potential ones. And of course those numbers work out to the same thing. What is the probability of getting a spade and an ace? Now, a spade and an ace, and you might think to yourself, what on earth does that mean? So let's go back to the previous page and let's look at it. There is a card that is simultaneously a spade and an ace. And here it is, the ace of spades. You can get a card that is both a spade and an ace. That card is called the ace of spades. And there is one of them in a deck of 52. The probability of getting an ace and a spade, that is the ace of spades, is 1/52. What's the probability of getting an ace or a spade? Now this becomes far more interesting, and I'm going to do this entirely in 50 seconds, at least initially, just because then we can do the arithmetic easily and we can see what's going on. So the first question might be, what's the probability of getting a spade? And you might remember from the previous page, the probability of getting a spade is 1/4 or 13/52. So the probability of getting that spade is 13/52. Now, that's not the only thing we're interested in. Our event space would be equally happy with an ace. And so you might say, well, what's the probability of getting an ace? There are 4 of them in a deck of 52. So the probability of getting an ace is 4/52. And at this point you might say, well, that's great. We might get a spade, in which case the probability of getting a spade is 13/52. The probability of getting an ace is 4/52. And if we add those up, we're going to get the probability of getting an ace or a spade. The problem is, and this becomes a big issue, and we'll talk about it in more formal terms, that we've counted a card twice. In other words, it's possible to be a spade and an ace. Take a look back at the previous question. You could be a spade and an ace if you are the ace of spades. Now, we've counted the ace of spades in this next question twice. We counted it once as a spade, and then we counted it again as an ace. So in other words, in that 13/52 among the spades is the ace of spades. One of these is the ace of spades. Similarly, among the 4/52, one of those is the ace of spades. We've counted it twice. Now, that's not fair. If each of the outcomes is equally likely, as is a prerequisite for doing this form of theoretical probability, we need for there not to be some outcomes that are counted more than others. So we need to actually subtract the ace of spades, that 1/52, the thing that is both an ace and a spade. So let's go through and do the arithmetic. 13 plus 4 minus 1 is 16/52. 16/52 simplifies to 4/13. What is the probability of getting a jack and an ace? Now, if you have the playing cards memorized, this question is almost comical, but I'm going to go back to the picture of the deck and ask you to find a jack and an ace. So let's see what's going on here. So here are the jacks. There's they are. There's 4 of those. And here are the aces. And we're pulling one card. So you might say, well, maybe we'll pull a jack, maybe we'll pull an ace. But can we simultaneously pull a card that is both a jack and an ace? And the answer is no, we cannot. So when we go back to that question, that is an event that is impossible. Hence, its probability is 0. We can write that as 0 divided by 52, which of course is the same as 0. Now, how is that different than the question about a spade and an ace? So let's compare these two. When we asked to get a card that's a spade and an ace, we said that happens. It's called the ace of spades. So let's go back and see where the ace of spades lives and how we could find it. So if we're interested in an ace, well, here are the aces. If we're interested in the spades, here are the spades. Notice that those two conditions overlap, and they overlap simultaneously at the ace of spades. The next question asked us for a jack and an ace, the next and question. And notice those don't overlap. You can't simultaneously be a jack and an ace. So when we answer that question, we're going to say, no, that doesn't happen. Okay, so what is the probability of getting a jack? Well, there are 4 jacks out of 52 cards. So the probability of getting a jack is 4 50-seconds. And then let's ask the question, what's the probability of getting an ace? Again, there are 4 of them out of 52. Now we have to be concerned, as we were before for an OR question, and that is we might be counting the same card twice, except we've just answered that question. We're not counting the same card twice because there's no way that you can be a jack and an ace. So I'm going to show this just to show where these ideas come from. We don't need to show minus 0 50-seconds because, of course, 0 50-seconds is 0. But I want to show that that and, jack and an ace, is exactly where it was in the previous time we looked at an OR question. In the previous OR question, we had to subtract the probability of being a spade and an ace. Here, the probability of being a jack and an ace is 0 50-seconds, but I'm showing that just for consistency's sake. So now let's go through and do the arithmetic. 4 and 4 is 8, take away 0, still 8, so 8 50-seconds. And then, of course, when we simplify 8 50-seconds, we get 2 13ths. Complementary events are what happens when something else doesn't happen. So the first thing we're going to talk about is the plethora of notation for complementary events within statistics. There is an absolute, just tremendous amount of choice. You could put a superscript capital C. You could just put the word not in front. You could put a tilde in front. You could put a bar on top. All of these things mean that we're looking for what happens when event A does not happen. Now, that bar may look familiar to you. We've seen a bar on a variable before. We had x bar, and in fact we'll continue throughout the semester to put bars on letters and talk about their arithmetic means. Notice that that A is a capital letter, so that's the event when we're looking at probabilities. Arithmetically, this means that if you add the probability of an event happening to the probability that it does not happen, you get 100%. You get everything. And I think this is relatively intuitive as well. Either an event happens or it doesn't happen. And if you say either an event happens or doesn't happen, you're kind of implying that those are the only two possibilities, that together that makes 100%. Either P of A or P of not A, those two probabilities added up is 100%. 1. That is everything. Now, if you do a little algebra or arithmetic and you subtract the probability of A from both sides, you can see that the probability of not A is 1 minus the probability of A. In other words, when A does not happen, that is the probability of not A, that's everything but A. And in fact, that's exactly what 1 minus the P of A says. Everything is 1 minus P of A. So everything but P of A is the probability of not A. So even that, without even considering the algebra, makes some, I hope, intuitive sense. Now, sometimes it's a lot easier to calculate the probability of not A than the probability of A. And our first example, and to my way of thinking, the best example of this, is finding the probability that a class has shared birthdays. This is a perfect example of it being a lot easier to find the probability that something does not happen than something happening. So it says, what's the probability that 2 students in this class share a birthday? So there's between 20 and 40 students in a class, 20 in those classes with support, and up to 40 in, or more than that, in classes without support. So first off, there's a lot of ways that this can happen. And think about that. 2 students share a birthday. Well, that's kind of sloppy English, but I think you'd agree that you'd be happy if 5 students in a class shared a birthday. That would mean at least 2 students share a birthday. So if we said this in much more precise English, we'd probably say, what is the probability that at least 2 students in this class share a birthday? So all of a sudden we have the possibilities when 2 students share a birthday, 3 students share a birthday, 4 students share a birthday, 5, 6, 7, 8, 9. You get the idea. And worse than that, those 2 students may be the first and the second, the first and the 5th, the first and the 29th, the 17th, and the 18th. So there's lots of ways that this can happen. So we're going to use this idea of complementary events to make this problem much easier. There is only one way of it not happening. So give yourself a second with that. We've just kind of imagined all the phenomenal number of ways in which at least 2 students can share a birthday. But there really is only one way that it doesn't happen, and that if everyone has a different birthday. So if everyone in class has a different birthday, we don't have any concern about the number of people who share a birthday because it is 0. So we're interested in finding the probability. Let's start with maybe not a class, but a group of friends. So 2 friends in a group of 8 share a birthday. And notice that here I've been a little bit more precise in my English. I've said at least 2 friends in a group of 8 share a birthday. So again, we're going to think about this. This is an example to my way of thinking of complementary probabilities. So we're going to say that this is the complement of asking, what is the probability that no one shares a birthday? So we're going to start this exactly the way you'd expect. We're going to start this with 1 minus, and we're going to do that because we're interested in finding the probability that no one shares a birthday and taking that away from 1 to figure out the probability that at least 2 people share a birthday. And here it goes. So remember, there's 8 friends. So the first friend, well, all we're interested in is that they do not share a birthday. So you say, hey, what's your birthday? And that person could say any date in the calendar. So the probability there, 365 out of 365. And then we move on to the second friend. And we say, hey, do you have a birthday that matches the first? So we ask for the second friend's birthday. And there's 364 days out of the year, out of 365, that they could say and not have the same birthday as the first friend. Now, then we ask the third friend. We say, what's your birthday? And they have 363 choices out of 365 that don't match the previous 2. And in other words, up to this point, we found the probability inside of that multiplication that 3 friends don't share a common birthday. But we were asked about 8, so let's keep going. So here's the fourth friend. Now, notice that a pattern is starting to emerge, and fairly obviously so. The first friend has a choice of 365 days for a birthday. It doesn't matter what they say. The second friend, well, there's 1 day that they can't say, or they'd share a birthday with the first person. So there's 1 choice taken away. They now have 364 days that they can say that won't have a common birthday. And then 363, 364. But all of these are out of 365. There's 365 days in the year, 365 birthdays to be chosen among. Let's see, we're at the first, second, third, fourth, we're at the 5th. We're now down to 361 out of 365. Here's the 6th, the 7th, and the 8th. A quick comment about the order of operations. Multiplication happens before subtraction. So all this multiplication has to happen before we do any of that subtraction. I only say that because we don't need to worry about parentheses. We're going to find the probability that 8 friends do not share a common birthday first. So that's all the multiplication. And then we're going to do the subtraction, the 1 minus afterwards. If you put this in your calculator, it'll do it exactly according to the order of operations. Our TIs know the order of operations. Now, this could be done in a calculator relatively easily, but let me show you a much, much easier way to do this. I'm going to introduce this just as an arithmetic shortcut at this point, but of course, and I'm sure you'll see that this is true fairly soon. We'll add this to our probability repertoire. I want to look just at those numerators, 365 times 364 times 363 times 362, all the way down to times 358. And I want to point out that there is a simple way of computing this, a way that you can compute it so that your calculator doesn't have an arithmetic overflow issue, all sorts of good things. And that's by using permutations. So here is an example of using the same symbol to denote different things. That P is not a probability symbol. It's not got parentheses. That P is a permutation. Notice that it is stuck between two numbers, the 365 and the 8. The 8 is the number of friends. That's the number of factors in here. 1, 2, 3, 4, 5, 6, 7, 8. So we don't have to count down to 358 or 357. We can simply say 8. This expression is read 365p8. It's the number of permutations, and it's in your calculator in the math menu and then over towards stat. And the TI, you'd enter the 365 first, then you'd go into the math menu, go over to statistics, down to that P symbol, and then press enter, and then enter the 8. And when you do that, you're actually able to get a humongous number without an arithmetic overflow issue. So let's clean up this expression. Notice that the numerator we've been talking about is 365p8. The denominator is 365 times 365 times 365 times 365, 8 times. Well, we can certainly simplify that. A number times itself 8 times is a number to the 8th power. And if you put this into your calculator, you learn that there's about a 7.4% chance that among 8 friends, at least 2 of them share a birthday. But we can do better than that. We can now ask this question for a class of 20. So maybe this is a class with a companion. So 20 friends. Now all I'm going to do here, I'm not going to show the expanded form of this. I'm going to go straight to the form using permutations and exponents. So before I show you this, imagine what's going to change. The number of days in the year hasn't changed. The only thing that's changed is the number of friends. So we're going to choose 8 friends, and the exponent is going to be 8. So, or is going to change to 20. So take a look and notice that those are the only 2 things that have changed. We're now looking at 20 students. We're looking at an exponent of 20. And when you put this into your calculator, the probability that at least 2 friends share a birthday in a group of 20 is about 41%. That's fairly close to even odds. That's kind of surprising. Probably not what you'd expect. Certainly not what I expected when I first saw this. We're going to continue in this way. Now that we've got a way to do this, you can go up in your calculator. You can grab that previous line, change the 2's to a 3, making the 20s into 30s, and you can compute this before I can finish my sentence. What is the probability that at least 2 friends in a group of 30 share a birthday? And before you do, even though it's relatively straightforward just to change those 20s into 30s in your calculator, make a guess. We went from 7% to 41%. That's pretty dramatic, going from 8 friends to 20. So let's work through this. And we see that we're now at 71% approximately. That's amazing. In a class of 30, there's a 71% chance that at least 2 of those folks share a birthday. Now remember, implicit in this is the idea that birthdays are all equally likely. I think anyone in medicine knows that that's not true. So this is an example of theoretical probability, something we can get out of our calculators relatively easily, something that's a little bit counterintuitive early in our discussion of probability, and also kind of interesting. It's not unusual for a family to have 2 members of the family who share a birthday. We certainly have that in my family, and you probably do in yours as well. You get up to the size of 30, and there is a really good chance, about 70%, that 2 members of your family share the same birthday. So our book next turns to vocabulary, and in particular the ideas of being mutually exclusive and the ideas of independence. These ideas are presented in terms of examples. The reason that this is important is we will return to these ideas and look at how it affects how we actually compute probabilities. You've already seen a little bit of that when we were talking about the probability of pulling a card out of a 52 card deck and having that card be a spade or an ace. And the moment we had that or there, we had the issue that we might be counting amongst the spades an ace and amongst the aces a spade. In other words, we might be overcounting. So these ideas are where we are heading. So first off, some vocabulary. Two events are mutually exclusive if they cannot happen at the same time. So let's look at rolling a pair of dice. Now there's an interesting kind of shortcut in the vocabulary here, so let me point out what rolling a 7 means. So if you're thinking about a particular individual die and you're thinking, well, it has a 1 on it, a 2 on it, 3, 4, 5, and a 6 on it, how on earth can you roll a 7? So when we say rolling a 7 or rolling an 8 in the next example, what we're talking about is rolling a sum of 7. Remember, we're rolling a pair of dice. So when you roll a pair of dice, you can look at the sum. And the sum could be as small as 2 and as large as, let's see, 6 and 6 is 12. So when we roll a pair of dice, we can ask the question, what's the probability of rolling a 7? Now, you can roll a 7. It's as simple as rolling a 6 and a 1, or a 1 and a 6, or a 2 and a 5. You get the idea. There's lots of ways to roll a 7. But we're asking an and question here. Notice that the next thing I want to point out to you is that we're not simply talking about rolling a 7. We're talking about rolling a 7 and rolling a pair. In other words, they have to happen simultaneously. What's a pair? So a pair is, I hope, exactly what you'd expect. A pair is two of the same number. So 1 and 1 would be a pair, 2 and 2, 3 and 3, 4 and 4, 5 and 5, you get the idea. Now, to roll a 7, one of them has to be different. A 7 is an odd number, we're adding up integers. So a 4 and a 3 is close as we can get to two numbers that are the same. But there's no way to roll a pair and roll a 7. So that means that these two events, rolling a pair and rolling a 7, are mutually exclusive. They cannot happen at the same time. If you told me that you rolled a pair and that you rolled a 7, I'd tell you that that cannot happen. Now let's change one thing. Instead of rolling a 7, let's talk about rolling an 8. So when we roll these two die, we look at their faces and we add them up, and it added to an 8. And again, it's an and question. We're saying that something else must simultaneously happen, and that is that among that pair, or among that 8, there is a pair. So we got an 8 and we got a pair. And of course, this can happen. It can happen if we roll two 4s. So a roll of 4, 4 totals an 8 and is a pair. So that is not mutually exclusive. That is, it can happen together. I'm not saying it has to happen. I'm saying that it can happen. We're basically talking about things, which is why we say not mutually exclusive. We're looking for those things that cannot happen. And if we say that something's not mutually exclusive, we say it can happen. Independence is the next big idea that we need to define and talk about. So two events are independent if knowing that one happens, that is, if the fact that one happens does not change or alter the probability of the second happening. So I know something's happened, and then I ask for what the probability of something else happening is, that second event. And if the first does not affect the other, if the first does not alter the probability of the second, then they're independent. So let's look at a 52 card deck, and let's look at the two events, draw a queen and draw a queen. And before you think, wait, that's the same event, we're talking about drawing these two cards from the deck. Now, how could this be different if we're looking at events that are so similar? In the first case, if you draw a card, we note whether it's a queen or not, and we put it back in the deck and reshuffle. Now, what does that mean? We put it back in the deck, we reshuffle it. So there were 52 cards, we put it back, there's still 52 cards. So that hasn't changed. Now, if we're interested in finding the probability of getting a queen, and we note that the first is a queen, the chances of that happening is 4 out of 52. If we put it back in the deck and shuffle it, there is a possibility that we could draw that same card again. And in that case, because we basically erased all the memory, all the physical memory of the fact that we drew a queen, and a particular queen, in the first draw. We put it back and we reshuffled it. And then we drew another card. Those two events are independent. And I hope you can see that that's not only arithmetically so, because the denominator is still 52 and the numerator is still 4, but that's also true because of the way we did this, the act of drawing these two cards. Now, that's very different if we draw two cards out of the deck. What does that mean? I draw one card out of the deck, I look at it, and I say, that's great. I put it down, not back in the deck, not reshuffled back into the deck, and I pull another card. The probability has changed because, for two reasons. First off, there's no longer 52 cards in the deck, so the denominator is different. Similarly, we're interested in drawing a queen, but there are fewer queens now. If there were 4 to begin with and we drew 1, there's only 3 left. So the numerator and the denominator has changed. By not putting that first card back, we have changed or altered the probability of the second event. So in that case, the probabilities are not independent. And as I promised at the beginning, this matters because it changes how we deal with probabilities. So the first thing we're going to look at is if two events are mutually exclusive, if they cannot happen together. So in this first example, A and B are mutually exclusive. We get 2 results when this happens. So notice that this next line is actually got a comma and an and it's not in parentheses, so these are 2 separate results. One is finding the probability that an event or another event happens. And if they're mutually exclusive, if they cannot happen together, then we simply add the probability of those 2 events separately. This is very similar to the question that we asked earlier about pulling 2 cards from the deck. If we pull a ace and a 7, say, well, you can't have an ace and a 7. Those are mutually exclusive, so we'd simply add the probability of pulling an ace to the probability of pulling a 7. But we've got another result as well, and that is the probability of A and B happening is 0. Now, your first response to that might be, cool, we've got a result that says, if I'm asked the question, what's the probability of these 2 events happening together, that is, and, is 0. And your second response is probably, well, that is obvious. They can't happen together. And if they can't happen together, then their probability is 0. The next case are when 2 events are not mutually exclusive. Now notice that that does not guarantee that they happen together. It just means that they can happen together. So in this case, we only get one result, and that is, again, for the probability that those 2 events that are not mutually exclusive happen one or the other. Well, one of them could happen, or the other one could happen, but we should take away the case where they both happen. And the reason is because we've counted that probability of A and B twice. In other words, that was inside the probability of A, it was inside the probability of B. So we've counted it twice, we subtract it once, so that we've only counted that overlap once. So you can also look at these as arithmetic formulas. You can simply say that this tells us how to combine stuff. So you can look at these conceptually, or you can look at these kind of mechanically. Now, the next examples come from rolling 2 die. And hopefully, even from that very first example where we talked about flipping 2 coins, and we said there are 4 possibilities when you flip 2 coins. Heads, 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 tails, tails, heads, and tails, tails. Not 3, but 4 different possibilities. And that's because order matters. A head followed by a tail is different from a tail followed by a head. And similarly, a 2 followed by a 1 is different from A1 followed by A2. They have the same sum, but they are different events. In other words, first die in all of these illustrations is that red color, and the second die is the green color. Now, you don't really need to think of rolling this one die and then re-rolling that same die. You could think about rolling two die, but in that case they'd have to be different colors. So you'd say, okay, one of the die, the red die, showed me this, and the green die showed me that. So I'm thinking of one and then the other, but if you had two different die of two different colors, you could get exactly the illustration that is shown. So we're going to go through and we're going to do this in a little bit more complicated setting, but it is exactly the idea of the two coins being tossed and looking at the heads and tails. So first off, what is the sample space? Well, that is the sample space. The sample space is all 36 of those possible outcomes. Notice that there's nothing special about 36. There's 6 choices for the first die and 6 choices for the second. 6 times 6 is 36. So each toss on each die, and that's shown above. What's the probability of getting a sum of 5? And I'm going to be scrolling up and down quite a bit, so I hope that's not too jarring. But I also want you to notice that in your workbook, in the last 2 pages of this chapter, you've got a page you could tear out that's got die on one side and playing cards on the other. And you can do this with a pencil if you do it softly enough. And you say, what's this? Well, I'm looking for a sum of 5. And so I say to myself, okay, well, it could be 4 and 1. It could be 3 and 2. You get the idea? It could be 2 and 3. It could be 1 and 4. So I'm looking for a sum of 5. And these are the ways that I can get a sum of 5. 1, 2, 3, 4 different ways that I can get a sum of 5. So when we go down to answer this question, we can say the probability of getting a sum of 5 is 4 out of 36. There's 36, 6 times 6 possible different ways of doing this. And that simplifies to 1/9. In other words, 4 times 1, 4 times 9, the 4's cancel. Now, another way of doing this, and I'll do this for the next example, is just to go diagonally across here. Notice that that pattern holds. If you go over 1, you're increasing the second die by 1. If you go up 1, you're decreasing the first die by 1, so it stays the same sum. What is the probability of getting the first die a 2? So let's see what that means. Okay, the first die is this red color. So it looks to me like the first dies, the red colored dies, are all 2 in this row. And that reminds us that these really are independent events. The face that's shown on the first die on the red die does not affect the face that's shown on the second die, on the green die. In other words, they're as good as 2 different dies. No information passes from one to the other. So for knowing that the first die rolled a 2 doesn't tell us anything about what the second die rolled. It could be a 1, a 2, a 3, a 4, a 5, or a 6. In other words, there's 6 possibilities where the first die is a 2. So that means 6 out of 36, and the division serves us well. 6/36 is another name for 1/6. The next question asks, what is the probability of getting a sum of 7? Now that's a little bit more interesting. Instead of highlighting each one separately, I'm going to show you, hopefully, that pattern you saw. The first way of moving from left to right is 6 and 1, then 5 and 2, then 4 and 3, then 3 and 4, then 2 and 5, then 1 and 6. So we can see that diagonal pattern there. That gives us a sum of 7. And notice that there's a way of doing this in each column. And there's 6 columns, so there's 6 ways of getting a sum of 7. 6 out of 36, well, we just saw that. 6 out of 36 is 1/6. The next question asks, what's the probability of getting a sum of 5 and the first die is a 2? So let's go back and look at that sample space. So I'm going to do this by looking at the overlap. It says that the sum is 5, So let's look at everywhere that happens. Here the sum is 5 with 4 and 1, 3 and 2, 2 and 3, 1 and 4. So there's a sum of 5. Now we're interested in the first die being a 2. And so here's the first die being a 2. And notice that there is overlap. In other words, it is possible for both of these things to happen. You can have a sum of 5, that's the diagonal. You can have a first die that shows a 2, that's the horizontal, and it overlaps at 2, 3. So this can happen. It only happens one way. We're interested in where both of these things happen, and both of these things happen simultaneously at 2, 3. So we notice that there's one way out of 36 for us to get a sum of 5 with the first die showing a 2. The next question asks, what is the probability of getting a sum of 5 or the first die of a 2? So notice that this almost looks exactly like the previous question, except the previous question was an and this question is an or. So now we're going to go back and we're going to say it's perfectly fine if the first die shows a 2, that's acceptable, or if the sum is 5. So let's go back and let's look again at the sample space. So here's the sample space again. I'm going to go through and highlight the sum of 5, and I'm going to highlight the first die shows a 2. Now let's do this in steps. So the first thing that it talks about is getting a sum of 5. So going back to the question, we see that there are 4 ways to get a sum of 5. So that gives us a probability of getting a sum of 5 of 4/36. We then see that there's 6 ways that we can get a first die that shows a 2. But of course the problem is exactly the problem that we had before, and that is that we have double counted. We've double counted 2, 3. 2, 3 has a sum of 5, and 2, 3 starts with a 2. So we have to subtract it. And that's exactly what we calculated in step E in that previous question. So we're going to subtract 1/36, and I'm going to highlight both of those 1/36 because they are the same number, not by accident but by design. That's where both of those things happen simultaneously. And because it happens simultaneously, we've counted the roll 2, 3, that is 2 on the first die and 3 on the second die twice. Once because it adds to 5, once because its first roll shows a 2. So we can then say, well, 4 and 6 is 10. 10 minus 1 is 9. 9 and 36 are both on the 9 row. In the numerator, 1 times 9, in the denominator, 4 times 9. The next question asks us, what is the probability of getting a sum of 5 and a sum of 7? So let's quickly go back and look at why that's not true. If you already know the answer, good for you. Let's go back and take a look at the table. So a sum of 5, well, we've got that shown. Now let's highlight a sum of 7, and those are all the possible ways that we can get a sum of 7. Now this question asks us what's the probability of getting a sum of 5 and a sum of 7. Well, there's no way that two numbers can add to 5 and simultaneously add to 7. You can see that these two highlighted bands do not intersect. They're mutually exclusive. So when we go back to this question, we can quickly convince ourselves that that doesn't happen. There's no roll on there, or pair of rolls on there, that has a sum of 5 and a sum of 7. And of course, we're playing this game again. Now we're going to look at the OR. So I'm going to highlight the differences between these two questions. The first one asks us for an AND, the second one asks us for an OR. Now hopefully you can convince yourself that when the two events are mutually exclusive, We don't have to worry about subtracting any overlap because there is no overlap. It does not happen that both of these occur simultaneously. So let's go back and look at the number of ways each of these happen. So first off, when we're looking at the number of ways that we can roll 2 die and have a sum of 5, 1, 2, 3, 4. So that'd be 4 out of 36. And then of course 6 out of 36 for a sum of 7. So we're interested in adding 4/36 to 6/36. And because there's no overlap, because these two events are mutually exclusive, we don't have to worry about subtracting anything. We simply rewrite this as 10/36. So our last topic in 4.2 is odds. They come with a definition. The actual odds against an event occurring is the ratio with the probability of the complement of the event over the probability of the event. Now, once you've got that as a decimal, convert it into a fraction and then write that fraction with a colon between it, a to b with the colon or a to b with the 2, and then just as simplified as much as you can. That's what integers with no common factors mean. The actual odds in favor is the probability of the event over the probability of the complement of the event, which is just the reciprocal. So if you know A and B, just swap their order and say that the actual odds in favor are B to A, as opposed to the odds against being A to B. Or you can go through and do the arithmetic again and rewrite that fraction in lowest terms, that is, with no common factors. The payoff odds against event A occurring are the ratio of the net profit, that is, if you win, to the amount that you bet. So the payoff odds against event A are the net profit to the amount bet. That concludes 4.2. Our next look will be at 4.3, conditional probabilities.